if you can't simulate data or generate data that would be applicable to the model. So you want to do ordinary least squares, and there's a bunch of assumptions in ordinary least squares. Then I'd say, okay, why don't you simulate a data set that satisfies the Gauss Markov assumptions? Why don't you simulate a data set that gives you a logistic regression? Why don't you simulate a data set that gives you count data, so-called Poisson models, which we won't talk about much in this class, and the like. And the question is, well, how would I do that? Well, some part of it is easy, okay? So let's take a linear regression. We have y, which is n by 1, equals x, which is n by p, beta plus an error, and beta is p by 1, and the error is n by 1. Okay. Now, what do you observe? You observe x, and you observe y, and then you do ordinary least squares. Okay. Well, how would you simulate this? Well, how would you get an x? Well, you can figure out lots of ways of doing x's. You can just sit there and come up with a bunch of x's, a bunch of rows that are p columns wide, and as long as the matrix you come up with is a full rank, that is, doesn't have multicollinearity, that could be an x. So I'll say easy to come up with x. Similarly, since you're simulating, you can say whatever beta you want, okay? So it's easy to come up with beta, and so it's easy to get x beta, okay? So in R, that might be x matrix multiply B, where you've specified B. B is a p by 1 vector. X is an n by p matrix. Okay, but unfortunately, that's only this part. How do you get epsilon? Well, you could say I'll just pick some. But here's the problem. Recall, okay, epsilon must be 1, 0 mean, conditional on x. 2, and this is for the Gauss Markov assumptions. We can change these. 2, the variance of epsilon given x should be sigma squared. 3, the covariance of epsilon I with epsilon j given x should be 0 for I equal not j. And the question is, how would you do that? So you give me a bunch of epsilons and I go, okay, how do I know that they have a 0 conditional expectation? How do I know that they were generated by a process that had a constant variance? How do I know they're independent? In fact, we find when fraudsters try to create invoices by making up numbers, it's really easy to figure out that these numbers aren't independent. They don't make any sense. In fact, it's even worse than that when they use what we're going to talk about later, random number generators. It turns out they're too random. It turns out invoices have certain patterns, and they're just really, really hard to simulate. So how would you get these errors? Okay. Well, one thing you could do is you could have some physical process that generates those errors. Okay. So you go talk to a physicist and say, hey, the gamma rays are coming down, and what distribution do they have? Are they independent? Can I make them zero mean? Do they have a constant variance? And the answer is yes, you can do all that. Takes a long, long time. The second thing, and this is relatively recent, you can buy plugins for your computers that generate real random numbers, physical random numbers. And they use basically quantum, what do I want to call them? Fluctuations in the mechanics in your computer, and they seem to be random. Or you can have a device where you know it really is random. And there are some devices that generate huge numbers of these based on radioactivity. Of course, these are down in basements with lead around them and everything, but those can be used as well. And that's relatively recently. Even 3 years ago when I was teaching this course, I really didn't talk about those because you couldn't get them. You can get them on Amazon now for like $200, not the radioactive ones. Getting physical random numbers is fairly straightforward, but that's not what I'm going to talk about because by and large, that's not what people use. Okay. So what they're going to use is called a random number generator. And I talked about one that's physical, but in general, they're called RNGs. Okay, random number generators. The first ones are physical. And these actually go back into the 1950s. I mentioned the physicists. The physicists were actually pulling down the impacts of gamma rays, recording when they come down. They knew what the distribution was what the distributions were from physical principles, and they put them in a book that the RAND Corporation put out, and it said it's something like 1 million random numbers. And that was the only thing that came from things physical. The problem with it is 1 million isn't very many random numbers anymore. It was back then. And two, if you started at some place and then just kept going and somebody else started somewhere on that same stream that you were using, they would get almost the same numbers. And so you would have to randomly pick the random numbers and use the random number generator to do that. It was kind of a mess and people really didn't do it. The second thing are called pseudo-random number generators. And I'll just write RNG. Okay. And until recently, these were by and large what people used. That is, you generate something using a pseudo-random number generator, and then you do a bunch of tests and you ask, are they independent? Do they have the same distribution? Do they have a mean? Do they have a variance? And so on. And there are lots of ways of generating these. And then the third method are called Quasi random number generators. And they're a little more difficult to describe, but I'll do it this way. A pseudo-random number generator, you can kind of be unlucky, and you would get something that doesn't look random sometimes. Just like if you toss some coins, you might get 500 heads in a row. Really unlikely, but it could happen. The quasi-random number generators are generated so ex post, they always look random. So ex post, they always look random. Those have both good properties and bad properties. I'm not going to talk about the quasi-random number generators. I want you to know about them so that if you're reading something and they say we use the quasi-random number generator there, you don't think, oh, that's a pseudo-random number generator or a physical random number generator. Similarly, I'm not going to talk about physical random number generators for the same reason, but you will see those used more and more, particularly in finance now. What I'm going to talk about are the so-called pseudo-random number generators. And I'm just going to refer to those as RNGs in this course. I'm not going to refer to the other kinds of RNGs. So, how do I get random numbers? Well, there are lots and lots and lots of distributions. How do I get the distribution I want? If I want a distribution, maybe I just want a mean and a variance and independence. Well, by and large, everything starts with uniform random numbers. So U01, okay, that is the random variable whose density is a square on 0, 1. That is, if you look at what its density is, let's call this X. Whoops. 1, 0, 1. And so uniform, that is the probability you get something in any little piece, any little delta X of a common size is going to be the same. Okay? And from that, you can generate all other random variables. So the key thing on all these is how do you generate uniform random numbers? Well, there are formulas for this. And of course, as soon as you hear formulas, you go, wait a minute, this can't possibly be random. Okay? And John von Neumann, who came up with this, and people were calling them random number generators, said anyone who believes that a process generated by a function is random is, of course, living in a state of sin. And people chuckled about that because he invented a lot of this stuff. But later on, what we've learned is there are things that fail because we're not using real random numbers. And that's really what this part of the lecture is about, is to talk a little bit about that. So, the typical random number generator looks something like that, this. You have a random number u, I, that looks like it is a uniform random number, uniform 0, 1, and it is a function of the past k values and a number m that I'll talk about in a minute. The simplest ones are of the form ui equals f ui minus 1 and m. And I don't know if any of you know anything about the modular arithmetic, but you can write this as alpha ui minus 1 mod m. Okay. If you don't know anything about the modular arithmetic, that's fine. Okay. All you need to know is there is some function that takes the last value, that m, and generates a new value. Oftentimes, it looks something like this. you have the last number, I cube it, okay? And then I take the middle digits out. So let's say it's a 64-digit number. I cube it, and I throw away 16 digits on the lower side and the upper side, and I take what's left over, and that's my new number, and then I convert that into something that's uniform by making it go between 0 and 1. Okay? So, random variables like this are often called, or generation are called congruential, and the one that I talked about that uses modular arithmetic is called linear congruential. And the problem with these is the following. So, first problem. These random variables can repeat. And when I say repeat, I don't mean you get a 2 and then some other time you get a 2, or you get a 0.2 and some other time you get a 0.2. What I mean is all of a sudden the sequence starts repeating. And so you've got 10,000 simulations, 10,000 random variables, and all of a sudden you start getting that same sequence over and over and over again. Okay? The amount of observations, or the amount of simulations that you have to have, or you have before you start repeating, is called the period of the random number generator. And you always want random number generators with long periods. And so you want to look and see, well, what is the period? Okay. How does a random number generator start out? Let's just say we have one of the form U1 equals F, U0, and M. And let's say M is of a size that you have a large period and you would really like this random number generator. Where does U0 come from? U0 is called the seed. So for a random number generator, you always have to provide a seed. And then given the seed, you get a sequence. And if you have the same seed, you will always get the same sequence. Okay? This is actually good for some things. If you're worried that your code isn't working, and you're using true random number generators, you sit there and say, you know, I don't know whether it is the fact that I really have random numbers in there, or that something is happening with the code. And so if you can use the same random generation every time, oftentimes that will help you key in on something. Oftentimes there's a default for the seed. So if you don't provide it with a seed, the computer will. Sometimes it'll look at the clock time. Sometimes, and more often, it will look at how long since the first time in this session you've asked for a random number generation. When that happens, sometimes in different sessions, you're going to get the same sequence of random numbers, even if you don't want them. So I try to always use a seed. And the seed I try to use is my birth date without slashes in it, followed by today's date. And there are probably other people in the world that have the same birth date and are trying to do it on today's date. But usually we're not working on the same stuff, and so I'm not going to worry about it. If it's really, really, really important, I'll probably go ahead and use a physical random number generator. Second thing, the simple random number generators here are not the best ones to use. You actually want things to depend upon more previous things, more seeds, if you will. And the best random number generators right now, and remember these are pseudo-random number generators, are based on the Mersenne twister. Those of you who are computer science double majors will just love this, because basically they're getting down there into the binary representation of the numbers, and they're doing all sorts of clever shifts and twists to generate the random number generators. Okay. So, do you have to do these on your own? The answer is no, of course not. These are all programmed up in R. They're programmed up in Fortran, C, C++, Python. I can't think of any system that doesn't have random number generators. Maybe the old COBOL didn't have it, but I think even old COBOL had it. There are some that have horrid random number generators. For years, SAS had a terrible one, SPSS, and I think SPSS still has a horrible one. Anything Microsoft had a horrible one. In particular, Excel had a horrible one. I think those have been fixed. I know the lower level languages for Microsoft, the F# and the like, have pretty good random number generators. But that's just pretty good, and you need to know whether they are really good or not. So if you get in a situation where maybe you really need a good quasi-random number generator, there's a set of programs that you can use to test them. They're called the die-hard programs. And they're modern versions of this, but die-hard was put together by George Marsilia, who was an old colleague of mine. And so I always like to point out his test. And he was the first one to show how bad random number generators, or the ones that I grew up with, really were. And they were really, really bad. So we would have things where, for example, we were testing independence, and we thought we had this wonderful test, non-parametric test for independence, and it just didn't work. It just didn't work. We were generating the independent sequences. And I talked to him one day, and he says, well, of course not. It looks like you have a really powerful test, and what it's identified is the quasi-random number, or that pseudo-random numbers are not really random. You know, what's the matter? Didn't you ever learn any mathematics when you were in grad school? He introduced me to the first of the die-hard tests, and they work really, really well. So far, there are no pseudo-random number generators that pass all of the die-hard tests. The Mersenne twister comes the closest. Okay. So, what are the functions in R that you should look at? Well, the first one is R unit. Okay, this generates n uniform 0, 1 random variables independently. Okay. You can also have R unif n, I'll say minus, and I'll write it the way, well, I think you can do it this way, -1, 4, okay? And this would generate n uniform -1 for random variables. So they would be uniform over the interval -1 to 4. Now, there is a little bit of a problem with random number generators for the uniform. Technically, the uniform can't ever take the value 0 and can't ever take the value 1. Okay? Most of the uniform random number generators I've seen can take the value 0 and value with 1, albeit with very, 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 very small probability. In some things, that's going to cause a problem for you. You should be able to take the log of a uniform random variable. Well, you can't if it in fact is 0. Another one that you'll be interested in is R norm n. Okay, and this generates n normal 0, 1s, n standard normals. You can also have R norm n, I'll call it MV, and that gives you n normal MV random variables, where V is the variance and is the expected value. Think of any distributions that you've ever heard of, and they're going to be in there. The logistic distribution, the Weibull distribution, which most of you haven't heard of, the Poisson distribution. Basically, any distribution, you're going to be able to generate the random variables from that. Also, there are multivariate versions of this. So if you want to generate something that's multivariate normal with a mean vector M and a variance covariance matrix V, it'll do that. There's also an easy way of generating a set of standard normals and converting those into a multivariate normal. And I very often do that instead of using the random number generator. So one other that we will use a lot is a discrete random number generator. Okay. And it's going to be sample x n replace equals either true or false. Okay, and the default is true. So if you leave replace out there, and so what this is going to do is it's going to take a vector x, and it's going to sample n from x, from equally likely with replacement if replace equals true. Okay. So let's say you had 20 items in X. Let's say they're 1 through 20. Let's just 1, 2, 3, 4, all the way up to 20. And I want to sample randomly 5,000 from that. Then it would go and it would reach in and would pull them out with equal probability and then put them back in. And then you would get that sequence. So you would get many of the x's repeated. You might not get some x's might not show up. Probably a rare event given what I just mentioned. On the other hand, let's say I had x equals 1 through 20. Okay. N equals 50. And replace equals false. The computer is going to say, I can't do that. Okay. After I've drawn 20 of them at random, and without replacement, there aren't any more left. You told me you get 50. Now I'm not going to do it. Okay. So do be careful of that. Okay. If you're going to use replace equals false, that is, you're going to do it with without replacement. You have to make sure that the number of x's is greater than or equal to the number you want. Okay. We will use this implicitly later today when we talk about the bootstrap. This is how you're going to get bootstrap samples. This is how you're going to get bootstrap samples when we do random forests. This is how you're going to do bootstrap samples when you try to get variances for complicated functions. You can take whole courses on random number generation. There is a very good book by James Gentle, for those of you who are going to go to grad school, called Computational Statistics. Probably 2009, probably a Springer book. And it does a very good job of talking about these issues. It's not something I would read for this course, but if you have some time in the summer before you go to grad school, or when you're out working in the world, you just say, you know, I want to know a little bit more about this, a little bit more about that. It's a book I would recommend by James Gentle. So what can you use random number generation for? You can use it for simulation. But you can use it for something else, and those of you in finance will be interested in this. In finance, you oftentimes have to do very complicated integrals. And as you probably know, most integrals cannot be done by hand. They don't have closed forms. So let's say you had a really awful integral. For the time being, I'm going to leave this univariate, but this works for multivariate too. Okay. And this integral is intractable. Okay. How do you go about doing it? Well, you can use Simpson's rule. Okay. You can use Gauss Quadrature. Those break down as soon as the dimension gets around 5. So if you have a multivariate integral dimension about 5, you're going to have problems. Those of you who've worked on finance problems, you do these integrals where the x's, if they're vectors, are the vector of all of the returns of all of the securities in the market. Okay? You're going to do integrals of those things. Well, Simpson's rule is not going to work. Gaussian quadrature is not going to work. But what I'm going to teach you is going to work, and in fact, it's what people use. So, say there exists g of x greater than 0, a density with support on AB. What do I mean by support on AB? It means that integral g of x dx from a to b is equal to 1. And g is strictly greater than 0 over that region. Okay? You could probably get away with g of x at a being 0 and g of x at b being equal to 0. But you don't have to do that. So let's say there exists densities like that. Well, of course there exist densities like that. They're easy to create. You could create a uniform density over AB. That would certainly satisfy this, and there are others. So let's say there exists such a density. Then I claim this is true. This is just our old friend multiply and divide by the same number. Would you all agree with that? I certainly would hope so. Now, G is a density. Okay. Fx over Gx is a random variable. So this is a random variable multiplied by the density, and so it's an expected value. So I could write this as the expected value of Fx Gx. Okay. Well, that doesn't seem very helpful until I say the following. How do you estimate expected values? You estimate expected values by taking sample means. So let x1 through xn be IID, random variables, with density Gx. Okay. So let's say somehow we have those. Okay. Let's let Zi equal Fxi over Gxi. Okay. Then E of Z equals E Fx over Gx, which is what we're looking for. And now I have this I equals 1 through n. So if I want to estimate E of Z, how do I do it? I say E hat of Z is going to be equal to the summation I equals 1 through n, Zi divided by n. Okay. So let me keep this stuff down here. Let me erase this. Let me erase this for the time being. We'll write it back up. So I have E hat of Z equals the summation I equals 1 through n, Zi over n. And now I ask the question, this is a random variable. What is the expected value of that random variable? That is, what is the expected value of Z bar? Okay. Well, that's the expected value of the summation I equals 1 through n, zi over n. The expected value of a sum is the sum of the expected values, so that's the summation I equals 1 through n, ezi divided by n. But the zi's are iid, so ezi is the same for all of them. So this is the summation I equals 1 through n, ez divided by n. And that's going to be n divided by n ez, which is simply equal to ez. Okay. So this says that E hat z is an unbiased estimator of E, and now I'll write it out this way, f of x, g of x. And let me erase some of this so we can look at it. Okay. So what that means is that these estimates, these z's, if I generated a bunch of them, let's say I generated 10,000 of them, each time I did n samples, so I get a sample of n, I calculate a mean, I do that 1,000,000 times, and then I look at the histogram of the z's, they're going to be centered at this true value. That's what unbiasedness means. Similarly, the variance of E hat z, okay, is going to equal the variance of the sum I equals 1 through n zi over n. Okay. Since the z's are independent, the variance of a sum is the sum of a variance, so this is going to be the sum I equals 1 through n, variance zi over n. That's going to equal in turn 1 over n squared, summation I equals 1 through n, variance of zi. And then recall that the zi's are iid, and so this is going to be 1 over n, the variance of, and I'll just call it the variance of z. Okay. And how would I estimate the variance of z? Well, you have a bunch of z's, and so you just do the sample variance. Okay. And so let's say that you have something that's unbiased, and the variance is very, very small relative to the size of the expected value. You would say, look, I pretty much have it. Okay. I have that integral, and I haven't had to do any calculus at all. So what this is based on, in essence, is the law of large numbers. As this n goes to infinity, the simulated expected value gets arbitrarily close to what you're looking for. Now, this begs the question, where do we get these z's? So let's go back and rewrite the problem. And of course, you already see where this is coming from. This is why I introduced random number generation, because you're going to use a random number generator to to do this. So we have, we want the integral a to b, f of x dx. That's equal to the integral a to b, f of x over g of x dx. G of x dx. That equals the expected value of the random variable g of x, f of x divided by g of x. Okay. Now, use a random number generator to generate n x's from with common density g. By the way, you control what f is. You can make f anything you want. This is any, g. You can choose any g you want. This is really, really neat. You can take g to be uniform over AB. Okay. You could ask the question, how many n's do I need to make the variance smaller than 300 times the mean? I just picked 300 out of the air. You could ask the question, is there an optimal g? And the answer turns out to be yes, there is an optimal g. Okay. You would like a g that looks fairly similar to f of x over that interval. Okay. In fact, if f was a density itself, you'd say, well, why don't I just simulate off x and ask what's the probability that I'm between A and B. So this is used throughout finance. This is called Monte Carlo integration. And why do we use it? Well, we try to get p-values for estimators that are really, really, really complicated. And the integrals just are not very easy to do. So Monte Carlo integration, you use it all of the time in inventory. So when we're doing big inventory problems, 100,000 products, and we're trying to balance how much of this one and that one to hold for how long, what's the demand going to be, you have to solve a variant of something called the newsboy problem, the news vendor problem, which I showed you earlier. Those integrals are really hard to do. We do them by Monte Carlo integration. Everybody does them like that. Monte Carlo integration is pretty much how we got to space the first time, and probably how we're doing it this time as well. So whole literature on this, useful to know. The key thing is you need a random number generator to make this work. So I will give you a homework, not this time, but probably next time. You have the homework for this time, where you have to generate a regression, and you'll get a lot of experience doing this, and then you will use the regression and the thing we're going to talk about later today, the lasso, to do what's called model selection. But before we go there, I want to talk about something else. Call this the bootstrap. I hope those of you who took 482 have seen the bootstrap. I know when I teach 482, I teach the bootstrap. I also teach the lasso, but I don't know what we're teaching this time. And I'm going to take just a really, really, really simple example, but it's one that drives people crazy. So I have yi equals xi beta plus zi gamma plus an error. So I just have two random variables. Okay? And you do ordinary least squares, and that's just great. And then I say, you know, here's the problem. For whatever reason, we need this statistic. Theta equals I'll say the logit just of beta divided by gamma squared plus beta. Okay? For whatever reason, I don't know why I would need that. It's just these are two complicated functions. Okay, so recall this is going to be the log of beta over 1 plus beta. So we assume here that beta is positive, divided by gamma squared plus beta. And I want an estimate of this. Okay. Well, the obvious estimate is theta hat equals log beta hat over 1 minus 1, pardon me, 1, it should be 1 minus beta hat, 1 minus beta, over gamma hat squared plus beta hat, where beta hat and gamma hat are the OLS estimators. The question is, how do you work that out? How would you ever figure out the following? What is the variance of beta hat? Okay. Now, for those of you who've taken a probability-based, a calculus-based probability course, you sit there and say, oh man, the change in variable formula on that is just going to be atrocious. If you did a little bit of asymptotic theory in 482 or in your probability course, you say, well, I could use the delta method. I could take a Taylor's expansion and approximate this, and that might work out fine. It turns out it doesn't. You need huge, huge samples for it to work. So I'm going to give you a method for doing this. Let me get rid of these. You'll remember the regression problem. Okay. And I'm going to talk about this very heuristically or intuitively. You have to always be careful of intuition because it can mislead you. You can't argue with somebody's intuition if they get a correct theorem and then are able to prove it by correct means. It's just however you got that was kind of amazing. So I could imagine doing this. Say I had 1,000 samples yi, xi, zi, I equals 1 through n. Okay? Let's say that I had that many samples. So I basically have the original sample that I did my OLS on, that I got this statistic. And let's say I had 1,000 more of those. Then I could say, oh, look, I could calculate theta hat 1 through theta hat 1,000. Those thetas are all estimates of the same theta. They're not unbiased. They are what we call consistent, so they become arbitrarily close to the true values as n gets large. And so I say, you know what I could do? I could just take the sample variance of those 1,000 samples. And that would give me a variance. And that would give me a variance for an estimator that was n long, but that had n observations. But you'd say, you know, I really have 1,000 times n observations. Shouldn't I use all those? That'll make the variances much smaller. And I go, yeah, that's right. You should do that. But then how do I get the extra samples to make this trick work? Well, here's the trick. This is due to a guy named Brad Efron at Stanford. Not exactly sure. Probably 1984. Maybe a little earlier than that. Maybe 78. Somewhere in that. And it has revolutionized statistics. And it's really the first thing that was enabled by computer science. So it's, in a sense, almost the first machine learning thing that anybody ever did. You could not do what I'm going to do without the without a computer. So xi is drawn from a population with a cumulative distribution function f. So maybe it's normal, maybe it's whatever. And in fact, here, I want to make this x, y, x, z. And it's from a joint distribution, y, x, z. Okay. And I draw n of those. I'm going to note something. We talked earlier about fn y, x, z, which would equal the number of yi, xi, zi that are less than or equal to the fixed numbers y, x, and z divided by n. This is called the empirical cumulative distribution function. Okay? And the interesting thing is that the empirical cumulative distribution function is very close to the actual one. This estimate is an unbiased estimate for each y, x, and z of f. And so you can't pull another 1,000 or another n observations from f, but I know what Fn is, so I could pull 1,000 observations or n observations off Fn. And then I could do the trick that I said before. Draw n observations at random from F, calculate the statistic, draw another set independently, calculate the statistic, and so on, and then average the results together or calculate the variance or calculate the skewness or whatever you want. And that's the intuition behind the bootstrap. And so I'm going to show you, in fact, how you do it. This is the intuition. The intuition will be useful to you later on. Not essential in this class, but the mechanism is. Okay. 1. Compute beta hat, gamma hat, beta hat. Okay? That's with the original data. Two, set B equal to 1. I'm going to erase this here. Draw yi1, xi1, zi1 from original data at random with replacement. Okay, this is called the first bootstrap sample. Okay, compute beta hat 1, gamma hat 1, theta hat 1 on this bootstrap sample. Okay? I'll write it out. Step 3. It's hard to do this on small boards. 3, B equals 2, generate a second bootstrap sample x2i, y2i, x2i, z2i, I equals 1 through n. So again, sample with replacement. So from the original data set, draw rows at random with replacement. By the way, when you do that, you will miss a whole bunch of observations, actually roughly 30% of them, and you'll have doubles and triples of others. The first bootstrap sample and the second bootstrap sample will be quite different. Compute beta hat 2, gamma hat 2, theta hat 2. Repeat. B times, where B is a large number. Okay? So now you've done this, and what do you have? You have beta hat 1, gamma hat 1, theta hat 1, dot, 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 beta hat B, theta hat B, gamma hat B, theta hat B, okay? And here's the idea. The variance theta hat is equal to the sample variance of the theta hat B's. That is, we would equal the summation summation B equals 1 through cat B, theta hat B, little b, minus theta hat, and I'll call it bar, that would just be the average of all those, squared divided by B minus 1. Okay. And I should probably put V hat, theta hat. That's called the bootstrap variance of this very complicated statistic. You haven't had to do the changing variable. You haven't had to really use any probability at all. And what it turns out is this turns out to be quite a good variance estimator. You will find variance estimates are hard. It's hard to get good variance estimates. The bootstrap does a very good job of it when the bootstrap works. Just like everything else, there's situations where the bootstrap won't work very well. One of the places where it won't work is anytime your objective function, like least squares, isn't differentiable at a point. And we'll run into a case like that soon. I hope you've seen the bootstrap before. In any case, it's really easy to do in R. There's a package that does the bootstrap, and you just say, here's what I want to do. And it says, okay, you give me the data, you tell me what B is, and you give me the function you want, or not even the function, the process you want me to follow. Then it can be quite a complicated process. Give me the end statistic. Just give me a function that gives me this end statistic. And then I will do the bootstrap. I will draw at random from the sample you gave me with replacement, and I will calculate this. How big does B have to be? Sometimes it has to be pretty big. Sometimes it has to be pretty big. Typically what I do is I keep calculating it until this doesn't change very much. Okay? So I'll calculate maybe 100,000 Bs. And then I'll calculate a few more and see if this changes. And if it doesn't, I say, okay, I'm done. Maybe I'll do 1,000, but for the problems I work on, my functions are oftentimes very much more complicated. This won't be a scalar; it will be a vector. So this will be a variance covariance matrix, and they're just harder to estimate. Anyway, this is the bootstrap, and we will use it when we do boosting, when we do random forests. I'll show you how you could, though people don't use it when they do neural nets. And I will show you how you could use it, though we don't need to use it, as you'll see, for the Lasso. So that pretty much covers all the tools we're going to use through the rest of the quarter. And now we're going to go back to where we started in the first lecture, to the variance bias trade-off, and talk about flexibility and variance. And I'm going to bring some of these concepts back, particularly what I did last time, where I started with a model that just had a constant and then expanded it and expanded it and expanded it to model the heterogeneity. And I ended up with all sorts of interactions of things. And it could be very, very, very complicated. Very, very complex. And so I'm going to do this for the linear regression. We could do it for the logistic regression. You haven't had a whole lot of time playing with logistic regression. So since you're more used to the linear regression and the concepts are roughly the same, the formulas are slightly different, but the concepts are roughly the same, might as well use something you're familiar with. So I have something of the form Y, which is an n by 1 matrix, equals X, which is n by P, beta, which is P by 1, plus epsilon, which is n by 1. Okay. Let's say you have a lot of P's relative to n. Then your degrees of freedom are relatively small. What if I had n equal to P? You have no degrees of freedom. What if I had n smaller than P? Well, you can't even calculate that. But what if I come and I say, yeah, it is true, X is n by P. But I know that only a handful of the columns of X can be non-zero. And I know this maybe from biologic first principles, that certain things can't happen together. Similarly, in economics, certain things might not be able to happen together. But you don't know which of those things are the relevant ones. And so I know that there are a handful. And so if there's a handful, then I can solve these problems. So say that only a small number of columns of X matter. You know, let's say 10. Okay. And let's say it's exactly 10, because I don't want to do the combinatorics here. So this is solvable. This says search through all n choose 10 possible models. And by the way, here when I have the n, this n is the training n. So from now on, implicitly, we have a test set in the background. So search through all possible models get the sum of squared residuals for each, and I'm going to call this sum of squared residuals test. Okay. Choose the model with smallest SSR test, or whatever your measure of loss is going to be. Well, I don't know if you remember your first probability classes. I remember mine. I remember if you tried to do 100 choose 10 and calculate that by hand, that was a pretty big number. Okay. Now let's say that I'm looking at, pardon me, not N, P. P is the number of variables. Okay. So only a handful of those variables. And so let's say I'm in a situation where N is 100,000, P is 100,000. So I can't do the regression, but I know only 10 matter. And so I go through all 10,000 choose 10 possible models and pick the best model. You can see that's not going to work out very well. That's going to take forever. We would like a better way of doing this. We would like a more principled way of doing this. So over time, people have come up with various ways of doing this. And I will talk about two of them, even though I'm going to say you don't want to use either one of these given what's happened in the last few years. You still have to know about this. Okay. So we want to select the columns to be in our regression. And over the years, lots of things have been done. This is called model selection. So choosing the X's to be in there is called your model selection. So here's the first one. Do OLS of Y on X. Compute the p-values for each t-test of each coefficient. And don't lie to me, for those of you who have done regressions and say you've never done this. And then what you do is you choose as the variables to keep those with p-values smaller than 0.05. That is, I look at each coefficient. If it's significant, I keep it. If it's not significant, I throw it out. And I know many of you have done that because I've talked to some of you about this already. And it's kind of the biggest mistake that people make. So do you all understand what I'm talking about here? You do a regression, you look at the regression results, and you go, not significant, not significant, not significant, not significant, 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 all the rest not significant. Just keep the ones that are significant, run another regression on them, and say, I'm done. Here's the problem with that. Let's say that all those tests are independent. Okay. Let's give them the benefit of the doubt. I can write it in such a way that they are independent. So say all the t-tests, t-stats are independent. Okay. So what's the probability that I make an error, a type 1 error? What's the probability to make a type 1 error? Well, it's 1 minus 0.95 is 0.01, right? So probability I make at least one type 1 error is equal to 1 minus 0.95 to the number of tests. So say you have 1,000, did I do 1,000 here or 100? 100. Say you have 100 t-stats, then probability type 1 error is equal to 1 minus 0.95 to the 100, which is equal to 0.995. That is, you have almost a 100% chance of making a type 1 error. This is called the multiple comparisons problem. And people screw this up all the time. People do this all the time, and it is just simply wrong. Why is it a problem? Well, it's a problem because of this. Why don't people know that it's a problem? Well, there are two reasons. One, nobody had given them an alternative for a while. The second one is that t-statistics were by and large developed to test a single hypothesis. F-tests were developed for a single hypothesis, not for multiple hypotheses, not for multiple comparisons, just for a single comparison. And that small point was lost on a lot of people. Not so much among statisticians. Statisticians knew about this, and this was driving them crazy. So some of them would say, you know, you simply can't do that. You pick your statistic, you pick your hypothesis, your null hypothesis, you test it, and you either pass or you fail. Regardless of what happens, you're stuck with that. You can't go and say, oh, these other things look significant. I wonder if there's another hypothesis here that I could look at. That's called data snooping. That's called model selection. And in the old days, it was forbidden. It was forbidden because you couldn't do it in a principled way without ending up with something like this. Now, what people would say is, okay, we can approximate the type 1 error. You can see what happens if you want your type 1 error in something like this to be like 0.05, then the t-stats you're looking at have to be something like 0.000005. Okay? They have to be really, really tiny t-stats for you to reject the null. Okay? You're not going to have much power. So, but when you think about this, you really don't care about the type 1 error. So let's say you're going to do 1,000 hypotheses, and I say, look, 100% of the time you're going to make at least one type 1 error. And you go, yeah, okay. But the rest of the time, I might not be making any type 1 errors. What I don't really care about the probability of a type 1 error. What I care about is how many type 1 errors I make relative to some golden mean or something. And that brings us to what's called false discovery rate control. And that was kind of the hot thing in the 90s up until the Lasso comes along, and even after that. I mean, people still do this. So recall last time I introduced you to the notion of decision theory. And so I'm going to put a decision here. And over here, I'm going to put the truth. Okay. And here is the null is true. Here, not the null is true. The alternative, I'll call it A. I don't want to call it A for a reason you'll see, so I'll just say not null. Okay. And on the decision, I have a null and a not null. And so again, I have that confusion matrix I talked about, but it's coming from a different point of view now. And let's say N0 of the hypotheses I test actually, the nulls are true. And let's say that N1 are actually not null. The truth is not null. And let's say that I get B of those right, okay, and I get A of these wrong. So the null is true, but I reject the null. And I do that A times out of N0. And so my decision of not null, I'm going to call that R. And over here, this is just going to be N0 minus A, and this is going to be N1 minus B, and I'm going to call this N minus R. Okay? Okay. What we're interested in is for the things that were not null, things that we said were not null, how many actually were null? Okay. And so we have what's called the false discovery proportion equals A over R. So it is this over that. Okay. And what would we like that to be? We would like that to be 0 over R. Okay. We would not like to falsely reject the nulls at all. We would like to control this. We would like to control this. We would like to say, look, I'll accept some mistakes, but I don't want them to be any greater than 5%. I don't want them to be any greater than 10%, or whatever we agree upon. Now, this means that there'll be some type 1 errors, but it says the proportion of them is going to be acceptable to me. The problem is, I don't know those, so I don't know the false discovery proportion. However, under some mild assumptions, I do know this. I know the expected value of the false discovery proportion, and this is called the false discovery rate. Now, where does the term discovery come in? Well, in this literature, if you reject something that you didn't expect to reject, that's a discovery. So the null hypothesis says, I believe this, and if you reject that, that's a discovery. And so when you reject a null that's true, that's a false discovery. That's a false discovery. So, as it turns out, you can control this. And I'll give you a process for doing it. I give you a reading in the, both from Matt Caddy's book, but if you don't have Matt Caddy's book, even though I think it's fairly well done in there, there's also a Wikipedia article that I put in there that's a little more elaborate, but it covers this stuff as well. And we have this. This is called the DQ rule. Right. This is for controlling false discovery rate. Okay. We're going to rank the p-values of all tests from high to low. Okay. So low p-values correspond to discovering things. High p-values, it's like, you know, it could happen 50% of the time. I'm not going to worry about that. And now let I star equals argmin, argmax, sorry, argmax I such that, write it this way, pi is less than or equal to I over n times q. Okay. Q is your acceptable false discovery rate. The PIs are the order statistics of the p-values, ordering them from high to low. And you find the I, the first I where this happens. You find the first I that happens, and that's your I star. And then any p-value that is less than pi star is an interesting discovery. We won't say that it is an accepted null, I mean a rejected null. We will say it's an interesting discovery. And anything with p-values higher than that has a is not a discovery. It's not interesting. Okay. This is the Benjamini-Hochberg procedure. Now, one of the problems with it is it assumes that the p-values are all independent. There is a formula that works even when they are dependent. And you can look at that in the Wikipedia article. 2 years ago, I would go into this in greater detail because we didn't have the double lasso yet. Okay. Let me state the theorem. So, theorem. If the p-values corresponding to true nulls are independent, then the false discovery rate of the DQ procedure I just gave you equals pi 0 over Q, which is less than or equal to Q, and pi 0 over pi 0 is a probability n0 over n, where we defined n0 above. Okay. The key thing is you're not going to know what this is. You're not going to know what that is, but you do know that it is less than 1. You do know that this is true, so you know that the false discovery rate is less than Q. And so if you say, look, I can live with a Q, then this false discovery rate will be fine with you. Q turns out to be very much like the significance in testing. It's 5% too small, is 0.001% too big. Well, it depends. And frankly, a lot of these should also be decided in terms of decision theory. But that would take us way, way, way beyond this course. It turns out this still isn't the right way of going and figuring out which ones of these x's are, in fact, 0. It's a lot better. So why did I teach this to you? Well, you're having an interview at McKinsey, and they say, we ran this regression, and those 24 variables are all insignificant. Why don't you throw them out? And the answer is, well, that gives you a really bad multiple comparisons problem. And your significance levels are going to be way off. And it's just not the right thing to do. The right thing to do is the lasso. And here's why. They might push you on FDRs. If I were you, I would, read a bit about FDRs. They're not really hard to do. You just take all the p-values, you rank them, and then you calculate that cutoff value, and you say, yeah, and if anything's below that, and you explain what the false discovery rate is. But the way we're going to do this from now on here is we're going to use the lasso. And to introduce the lasso, I'm going to introduce the whole notion of regularization of an optimization problem. So remember what we're doing here. What we're trying to do here is figure out which of those x's do not belong in that regression. Okay? And then maybe to concentrate on the ones that we are interested in. So remember what ordinary least squares does. We look at min, beta, summation I equals 1 through n, yi, I'm going to write beta 0 minus, I'll do it with x's, xi transpose beta squared. Let's say that P is greater than n. Well, then this doesn't have a solution. This doesn't have a solution. I'm going to write this in matrix form. I'm going to write this as y minus x transpose beta, x beta, pardon me, transpose y minus x beta. Okay, that's the matrix form of that minimization. And I'll say, and over here it's beta 0 and beta. And what I did here is I just added another column for the x's of all ones, and I subsumed beta 0 into beta. I want to work with this for reasons you'll see. Okay. But now I'm going to do the following. I'm going to say min beta y minus x beta transpose y minus x beta. And I'm going to say, I'm going to subject this to beta transpose beta is less than or equal to s. Okay? Beta transpose beta is less than or equal to s. This is called a regularization. So I put some restrictions on the beta. This takes these betas and it shrinks them towards 0. Now, why might you want to do that? Well, with ordinary least squares in this form, it says, you know, beta can be anything. Beta can be infinite. And you say, well, there's nothing that's infinite in our models. I know there's some bound s for which this has to be true. And so I'm going to impose this and I'm going to try and find that s. I should have asked you guys this before. So send me a note after this lecture. How many of you know what Lagrangian multipliers are? For those of you who do, you'll see exactly what's going on here. For those of you who don't, I'll write up a little thing on Lagrangian multipliers. They're not really very hard. So, as it turns out, this problem is equivalent to this problem. Min beta y minus x beta transpose y minus x beta plus, I'll call it lambda s. So there'll be a one-to-one relationship between this lambda and this s. Summation I equals 1 through n beta I squared. Okay. And I'll write this in the, no, I won't write it in the non-matrix form. It turns out that this always has a solution. This has a solution if you have multicollinearity. It has a solution if n is greater than, if p is greater than n. It always has a solution of the following form: beta hat equals X transpose X plus lambda S times the identity matrix inverse X transpose Y. And for those of you who have ever seen the ordinary least squares estimator in matrix form, if lambda S equals 0, then beta hat equals X transpose X inverse X transpose Y is OLS. Okay. So this estimator with this scalar lambda in there is called the ridge regression. And it always has a solution. And it was the first of the regularization estimators. It comes to us from physics. It was called the Tikhonov regularization, and it was for handling what are called ill-posed problems. And so sometimes, in particular in the communications literature, you'll say, yeah, we did a Tikhonov regularization on this regression, and blah, 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 blah. And you go, they did ridge regression. Okay. So this is nice. You get a solution. Here's what the problem is. It doesn't tell you what betas should be 0 and which shouldn't. In fact, you won't get any betas that are equal to 0 with this. You might get them that are very close to beta 0, but you won't get them equal to 0. First thing. Second thing, this restriction biased everything towards 0. And so you might end up with a whole bunch of things, even if you could calculate the variance. How could you calculate the variance? With Bootstrap. Calculate the variance of this, and you're going to find they're all biased towards 0. And so let's say that you find something is statistically insignificant. Is that because it's really insignificant, that the underlying beta is 0? Or is it because your estimator has been biased towards 0? Now, what this does do is the following. Typically, the MSE, and I'll call it Y hat ridge, is smaller than MSE Y hat OLS. Not always, often. Okay. So let's not say typically. Let's say often. So if what you're looking for is out of sample prediction, the ridge regression can do a good job for you. We have a problem here. What's the problem? We've got that parameter, lambda, and we'll forget about the fact there's an S there. Once we had the theta, the lambda, we could calculate back and find out what S was implied. They go together 1 to 1. What do we call these kinds of parameters? We've talked about them before when we talked about K and N. We call them tuning parameters. So this is a tuning parameter. And how do we handle tuning parameters? Well, we have we split our sample into 10 parts, and then we do k-fold cross-validation. So we estimate this 10 times for each lambda. So we start with lambda as close to 0 as we can, the ordinary least squares, and keep increasing it, right, until we get to a point where I think this, I forget what this ends up being as that goes to infinity. I think ends up just being a constant. In fact, it ends up being 0. I should mention something. Typically, you don't apply the restriction to the intercept term. So you just leave the intercept term off. And in that case, the ridge collapses to a constant. So it's OLS then to a constant. Okay? So OLS is very, very, very flexible. A constant is very inflexible. The constant will have a very low MSE, or at least variance, but a high bias, and vice versa. Ordinary least squares may be unbiased, but it'll have a big variance. And so the question is, are you willing to give up some bias to reduce the variance, to reduce your mean square error? So the ridge regression was used for a long time, but in terms of getting predictions. And remember, what I'm interested in, I mean, prediction out of sample is great, but I'm more interested in inference. And what I want to know is I want to get rid of any of the x's that don't belong in here. That is, any of the betas that should be 0. So the next thing that happens is this. People look at this and say, this is, oh, I don't want to use that. This is min y minus x beta transpose, whoops, x beta transpose, y minus x beta plus, and I'm going to write lambda, just plain old lambda. And then I'm going to write this as the L2 norm of beta squared. Okay? That is, take the square root of that, and you've got the L2 norm, the Euclidean norm, and I'm squaring the Euclidean norm. I'm seeing this isn't showing up very well. Let me rewrite it. So I have min beta y minus x beta transpose y minus x beta plus lambda, the L2 norm, the Euclidean norm of beta squared. Somebody looked at this, and this is how mathematicians think. They go, well, why did you use the L2 norm? Aren't there other norms? Isn't there the supremum norm, the maximum norm? Isn't there the L1 norm? What would happen if we used the L1 norm? And I'm sure that Bob Tibsorani, when he came up with this, that's exactly what he was thinking. Yeah, I need a PhD thesis. Everyone's done this. I wonder what happens if you use another norm. And so he looked at this problem. The L1 norm. And recall what the L1 norm is. That's the summation I equals 1 through P, absolute value beta I. Okay. This is a convex function, although it's not strictly convex. Why isn't it strictly convex? It's not differentiable right at 0 there because of the absolute values. And so sometimes you can get multiple solutions. Nonetheless, this estimator is called the Lasso. So, I've gone over, haven't I? Let me just, I can stop here and we'll come back next time. Beta hat Lasso equals argmin beta y minus x beta transpose y minus x beta plus lambda, and I'll write it this way, summation I equals 1 through p, absolute value pi. Now that's called the Lasso. And I'll come back and talk about this next time, but what the Lasso does, interestingly, is things that it sets to 0. So the Lasso will actually give you real zeros, machine zeros. What the Lasso does is if the Lasso beta hat, if any one of them is 0, then with very, very high probability, in the sense I'll describe in the next lecture, you can be assured that the true coefficient is 0. And so anything where the Lasso has a 0 coefficient, you can throw that variable out and be absolutely sure it doesn't belong, and you're not making any type 1 errors, you're not doing any multiple comparisons. In fact, what you're doing is, this is a clever way of going through all those 100 choose 10 or 100 choose however many models that I talked about in the beginning of the lecture. It does have the problem that the betas that are left over are biased towards 0. So I'll come back here next time. This is going to be our workhorse, and this is the thing that solves the multiple comparisons problem, solves the problem of looking down a bunch of t-statistics to see what's significant and not, and making bad type 1 error decisions, and not having to deal with false discovery rates. So we'll come back and talk about that next time. And we're going to talk about this for a fair amount. Obviously, there are computer programs to do this, and they'll even do the cross-validation for you. So this will be great. And then I will show you actually how you get something equivalent to unbiased betas by doing what's called the double lasso, which my colleague Victor Chernzukov, my colleague at Amazon, he's a professor at Northwestern, he came up with this a few years ago, he and his student Alex Bayoni. Okay, that's it for tonight. The Lasso and the Bootstrap are the key things from this lecture.
Okay, so I'm going to share a screen for this week pre-session. This week, as Professor just talked about, like he talked about like Regression and Lasso, and then he will cover the difference between these two methods next week. And then, so I'm going to introduce the multinomial logic and how to render regression by using R in this case. And so the first thing here, I just want to let you know that we have a mid-quarter course evaluation, which this is the link. And the reason for us to let you fill out this form is just help us to improve the online teaching process. This is first time, and we wish we could do better and help you to learn more. So please fill out this form if you haven't done it, and it will close tonight by the midnight. Okay. So any question before I start? Any question regarding the lecture or previous quiz session things?
I have a question. The professor mentioned on Monday there would be a homework set that would be posted on Monday, and then it wasn't posted.
Yeah. Okay. So I'm not sure. I mean, like, he told me he will post it by the end of today, but I will send him email to let him know that he haven't posted yet. So it will do next Wednesday, I think. Okay. I will let him know.
Okay, thank you.
Any other question? Okay. So if you don't have any other question regarding lectures, I'm going to start this quiz session. So the first thing, as we have done before, is how we install the package. So this week we are going to use the data from this package, and you can use this line to install the package. So just uncomment this line, and then you can run this one on your R. And then so most of the things, first of all, we are going to talk about like multinomial logic regression. And I'm going to give you several examples about like why we are using multinomial logic regression. And the first one is just people's occupational choices might be influenced by their parents and their own educational level. So in general, we used to use logic regression to talk about like binary choices when we have either you want to buy the eco labeled apples or not. So that one is in general we use the logic regression to run regression for that one. And then when there are multi choices, like for this one, like people's occupational choices, you can choose whatever you want. Like you want to go to academia, you want to be a professor, or you want to go to industry, like you want to do consulting, do finance analysis, or you want to do coding, CS, software engineering developer. So all of these things are influenced by the parents' occupation and their own educational level. So in some cases, they are influenced by those factors. So we want to use multinomial to talk about to get the causal relationship between the choices and the features. And the second example is just a biologist may be interested in food choices. So also those choices may the type of food and predictor variable might be the size of alligators and other environmental variables. So all of these things, there are a lot of things can influence the choices of the food. So in this case, we use multinomial logic model to predict whether you will choose what kind of foods in this case. And the third one is just like high school students make program choices among general program, vocational program, and academic program. So, and then those programs are, so they will choose the program based on writing score and the social economic status. So in this case, just like remember when you are high school students, and then whether you decide you want to go to college and which program. So all of these things are influenced by the score, influenced by the parents' educational level and other factors. And then each time you make your choices, it does not like, so when you choose, like for example, when you're like UW, Washington State University, and then you can say something like MIT, so these three schools, and then you choose one of them, you will need to forgive the other two. So in that case, that means every time you made a choices, and then that's seems to be a dummy. Like when you choose one, then you need to forgive the other two choices. And then in that case, we use multinomial logic regression to focus the results. Okay. And so that's the why we are using multinomial logic regression. And then the data sets we're going to use is this now small data sets. This one contains 8 variables, and we are interested in this one. If the person will choose, if the post-secondary education was no college, 2-year college, or 4-year college. And then we are interested in these choices, how the person choose if they will choose like no college or 2-year college or something else. And then we have 7 factors here. This one is if it's Catholic, if it's a Catholic high school graduate students, and then the grades about average grades in math, English, and social studies, all of these things. And then one is the highest one, so it's not like in the general case. And so 13 will be the lowest one. And so this one is a family income, and then family size. This one equals to 1 if most educated parents graduate from college or had an advanced degree. This is dummy variable. This is dummy variable. This is okay. So this is about the data sets. And every time when you try to check you can, so like data sets, we use this one from package. Let's see the package. So you can always go to this part and then check this one. So after you click this one, you can check the data sets, which is here. So this contains all the information regarding data sets and the source. So here's the thing, after we run this one, we are going to use like we have done before, we generate random variable, random uniform numbers, and then use that one to divide the data sets into the train and test sets. So as we have done before. And then we're going to train the model based on the data sets. So we try to expand the choice of secondary institution by high school grade and the family income. So we will take 2 factors as the independent variables, and then the dependent variable will be the choice of a secondary institution. And so this one, as we have done before, we will attach the train sets here, and then we do the model matrix one. This one, in general case, it creates a design matrix by expanding factors to a set of variables. So you can check. Let's write this line first. So let's check what's the results for. So you can see so when we check the results, and when you do model matrix, the secondary choices, we run this one on the grades and family income. We'll give you an intercept and then the grades family income. So this function, in general, we use this one to create dummy variables. So think about when we don't run grades here, we have the states variable here, maybe Washington, Colorado, and then like other states. So all of these states are going to be changed to dummy variable, and then so because this methods only take numbers, it cannot take any qualitative variable into the model. So we want to transform all the qualitative data into numbers, and then we run the regression, use this line to run the regression. And before that, I would like to talk about the GRM net. method. So this one is going to fit a GMM with Lasso or like other regularization, like contains Gaussian, binomial, Poisson, and then multinomial and other. So you can predetermine the distribution for the regression. And then you can also specify if you want to run Ridge or Lasso or other things, you will use this function, you will use this method again and again. So we will talk about like how to use this one to run a Ridge regression next week. Okay. And then so for now, I'm only going to talk about like multinomial regression here. So we have family equal to multinomial, and then the lambda here is the tuning parameter like we have introduced before. So the let's see if it has the equation here. So in general case, we would and another thing here is important thing is the alpha here. So this alpha is going to play an important role when we talk about the Ridge or Lasso regression. So when alpha equals to 1, this function is actually going to be changed. So you will get rid of this part, and then only leave with alpha times the norm 1 of beta, which is Lasso regression we just introduced. And when this alpha equal to 0, we are going to get rid of this part. So we will leave with the Ridge regression, which is 1/2 of the norm 2 of the beta. And so the lambda represents for the tuning parameter, which in front of the penalization, which we have introduced in the lecture. And then in this case, when we talk about the multinomial, we do not actually want to have the tuning parameter here. So this one we will set lambda equal to 0. This C0 is actually so when you talk about C0, it just give you a number with 0. Element in the list. So let's run this check. Okay. So this will be the results for the coefficients here. And then this one. This one is like the model matrix function. And then this one shows the coefficients for the multinomial regression. The reason we doesn't have anything here is just because we set the second choice as the benchmark. So everything here will be modified based on the second choices. And then how it's going to change from the second choices, and then those number represents for the coefficients in this regression. And then similar as before, we are going to predict out of sample. So we are going to apply this methodology on the out of sample, which is the train data, testing data here. So you can see the testing data contains 250 observations. And then we train the model actually on the data sets with 750 observations. And then the interesting here is when you assign different tab here, this will give you the results, actually the choices of the secondary school. And then this one response to give you the probability directly. So let's check. So you can see for each of the observation Y here, it gives you directly the choices for the person, like which the person will choose which kind of we choose which choices for their secondary education. And then this response one. So you can see when we have the Z variable here, when you tap response, it will give you the probability for the person to attend to each of the choose which choices in this case. So you can see here for the first person, the probability for go to with no college is 20%, and then for the college, 2-year college is 30%. And then this one is the highest one, so they will classify this one. This person will go to the go to a college, 4-year college, and then you can see here label Y here. The first number in Y, first element in Y is 3. So that's how they classify each person with their choices. Okay. And then similar as before, we do the table, compare the table, and then we check if the accuracy of the predictions. So here's the deal. So you can see here we have the prediction for the prediction results predict the person will choose the first choices, which is the no college. So there are like 29 correct predictions when the true is 1. And then it predicts 116 observations as choose for them is to go to a 4-year college. And the prediction is 4-year college as well. And the rest of those are just false prediction. And then when we try to talk about the percentage, we got 58 correct predictions based on the sample. Okay. And then this one is just help you to check the accuracy of your model, and then based on the out of sample data sets. Okay. And that's how we run a multinomial logic regression in this case. So any questions so far?
Yeah, I have a quick question.
Mm-hmm.
Why is it not a 3x3 table? Couldn't it predict all 3 alternatives, or we just have 2 alternatives?
Possible the prediction does not contain any 2. So in this Y, you can see there's no 2 here. So they won't result in any prediction for a value equals to 2. So there's not 3x3. Because when you add a 2 here, it will be 0, right?
Okay, thank you.
Good question. Any other question?
I think that the question was why we need a benchmark for the 2.
Because every time when you, even though when you do the logic regression, you still need to have a benchmark. Like you are going to like choices. So once you make your choices, you will choose 1, and then there will be 2 alternatives, right? So like when you face 3 choices, you will choose 1 of those 3. And then when you choose, when we run the regression, you will have 1 as the benchmark, and then test how the results will going to shift from the first one to the 2 alternatives. And then in that case, it's even in the logic model, like when you choose either you want to buy the apple or not, and then you will going to test in which case the coefficient, the results will shift from 0 to 1. It's the same thing as before. Does that make sense?
Thanks.
Sure. And so the other thing I'm going to talk about today is the conditional logic model. So this one is more like a theoretical based part for this quick session. Like remember when last time we talked about like the discrete choices for each person. And then, so this one is based on the utility for the S individual choosing case alternative. Remember these discrete choices we introduced last week. So why we are going to use the conditional logic? In multinomial logic model, all individuals face the same external condition, and each individual's choice is only determined by the individual's circumstances or preferences. So no matter you want, so like remember the example, like the example we just talked about, like if you are going to go to a college, 2-year college, 4-year college, so all the other things are not going to be changed. But for this case, the conditional logic model allows for individual to face individual-specific external conditions, such as the price of a product. So like when the person in Seattle and the person in Tacoma, they were going to, like, when they're going to buy an Apple, they are going to face different choices. I mean, I'm sorry, face different prices. Like the price from the price may be different for these two places. And then in that case, we are going to introduce the conditional logic. So we consider the observed part of the utility as individual choosing the case alternative. So we denote this utility by U sub ik here. And then this one, in this model, Latin letters X, capital X, Y, and Z stands for the design matrix, while the Greek letters stands for the coefficients. So you can see the difference here. This one is going to be very varies based on the person, like if it's F person or like case person, something like that. And then all these things are going to be with different subtitles. So all these little these variables are going to be changed based on if it's going to only change based on the person or based on both person and the alternatives, or it's not going to be based on either person or the choices here. So for many practical application, variable in multinomial logic model can be naturally grouped into two types. So individual specific variables, which do not vary between choices, like the income. No matter you are going to buy an apple or an orange, it's still the income will be the same. And then for the alternative specific variables, Y and Z, this one may vary with alternative and may also differ between individuals. And then, so in the example we are going to use will be the amount of fish caught in the data. Okay. So it's going to be more, it's going to be much clearer after we introduce the example later. So let's first just load the data here. So the data frame in the package, so we are going to use this package. And the data in this package is called fish. It contains 5 observations, 5 variables. The first one is going to choose the regression mode choices, one of the 4 of those choices. And then the price for mode for an individual. And also the catch. This variable is we have introduced here. It's going to be vary based on person and the alternative. So the fish catch rate for a model for an individual, and the income for an individual. And then this one is just the chooser ID, which is just an identification number when we do the analysis. So consider a multinomial logic model where the price has an alternative independent coefficient, intercept, and so this one independent coefficients is the price of a mode. And then this one is not going to be it's not going to be changed based on the person and the alternative. So it does not have any subtitles here. And the intercept and income data is going to be individual specific. So it's going to the income for each individual is going to be different based on the person. And then the catch, this variable has alternative specific coefficients. So this one is like this one, the catch rate will be based on the person and also based on the choice of the mode. Okay. And then, so we have 4 variables in the model. So we are going to use have 1 for the price, and then we are going to have 6 for the beta k, 3 for the intercept, 3 for the alternative income here. So remember, like when we we have 4 for the catch rate. This one is based on both the individual and the regression mode. So here we're going to introduce the formula function here. This one is mode run. We want to run the regression of mode on price and income and catch. And this one, the reason for me to have this little sign here is just because we are going to run the mode on different kind of income based on different kind of catch rate. So it allows us to vary, to change between among the alternatives and change among the person. And this line is how we run the conditional multinomial logic regression. So similar as before, I'm going to show the code. So here is the here's the results for the regression. So when we do this line, we are going actually, so this one, let's introduce just line by line. So the frequency of the alternative in input data is just 4 kind of the regression mode. And when you sum these 4 numbers together, this one should equals to 1, because it talks about the frequency of the alternatives. And we have, so you can see here, we have 1,182 observations in the data. Like you can see, the original data we have is 4,728 observations. The reason for us to go into like 1/4 of the original observation is just because it's a long form data sets. Remember the professor posted the difference between the wide form and long form data sets on Canvas. So this is long form, which means each person for the choices, if they choose speech, choose both, or choose others. So there are only one choose among these 4. The person will only choose one of those 4 modes here. And then actually there will be only 1,182 persons in the data sets. And number of alternatives is 4, which depends on the number of modes. And then number of parameters in the model is 11. So we have introduced before, this individual specific variables. This one is the intercept and the income for each person. And choice specific coefficients income. This one is the based on each mode here. We have introduced the regression mode. And the individual independent variable, this one would just be the price here. So we have here we have 11 total. So you will have 11 parameters in the model. And then we are going to, this regression method use maximum likelihood estimation based on the Newton-Raphson method. And this one we have covered before about how to, so you don't know specific things, like we won't ask you to derive all the things, details in the model, in the method, but you need to have a roughly intuition about like what is a maximum likelihood estimation. Roughly speaking, it's just over, as we have more and more observations, we're going to have a likelihood function. And then after we sum those likelihood values, and we can get the estimation parameters based on the Newton-Raphson method. So here's the model, here's the estimation results. There are 3 intercepts value. So for each of the intercept, for each mode, the intercept will have a value for the mode. And then the income will be based on the person. So there are 3 income here, 3 kind of income here based on the beta k in the model here. This beta k in the model. And then for the catch one, this one is based on both the person and the alternative. So there will be 4 here, as we have talked about before. And then 1 price. This one is not going to be changed based on the person. So it's only 1 estimation of the price. And you can see if it's a 3-star, then it's significant level. It's significant at the 0 significant level. And when it's double star, it's significant at the 0.1% significant level. So you can see how those estimations are like significant in the model. Okay. And then this one reports the log likelihood value. And then this degree of freedom is 11. It's equal to the parameters. And the archive information criteria just how does the model perform in the data sets, if it's a good model or if it's a bad model. And then this one is kind of, you can use either archive information criteria or like Bayesian, like BIC criteria. Those things that just give you an intuition about like how does the model perform in the data set. Any questions so far? Okay, so this is how we run the regression, how we interpret the results. And then by the default, we're going to talk about like how we change the model. So by default, the intercept is included. Like you can see, we have the intercept here. But it's possible to be omitted by inserting -1 or 0 anywhere in the formula. So you can see here, when we use price -1 here, it actually does not have intercept. So it's only type 1 with no intercept here, without intercept here. And then we can also omit any group of variables from the model by placing a 1 as a placeholder. So when we place 1 here, we will run the regression of mode on income with the intercept. So we are not going to run this one on the price here. So you can use 1 to replace the variables from the model. I'm not going to run this part. It's just like in case you want to run different kind of regressions. And then similar as before, we do the prediction accuracy on the testing data. It's not changing. So we do, first of all, we are going to pull the choices out of the model. So you can see here, we have there is only one choose out of the 4 for each person. So first of all, we are going to pull the true out of the first column, which we run this one. And then let's check the fish sub. So fish sub table contains the true model for each person. And then all the false model are going to be eliminated from this data set. So there will be only 1,182 observations in this data set. And then we are going to pull we are going to do the prediction here, which we predict the I'm sorry, this is actually training. I don't remember what I wrote. So we're going to test on the sample. So we predict the sample itself. And the probability equals to false, just let them to give us the alternative directly, rather than give us a number or like probabilities. And then we do table and then do the min here. So you can see here, the column, this vertical axis represents the predictions. So when we predict people will go to the beach, actually there are 24 persons go to the beach in the true model, in the true data sets. And then all those diagonal values are going to be the true correct predictions. And then all the off diagonal values are just false predictions. And then you can see we have like 47.8% correct prediction in this case. It's not, I mean, like, it's not a good prediction, but just give you a taste of the model, like how we do the predictions based on the conditional logic model. Okay. Any questions so far? And you can always apply the prediction function onto the testing sets and get the out of sample predictions. And so the last part, I'm just going to have you to review the algorithm for the linear discriminant analysis, because this is kind of not that clear from last week lectures. And then I got a few questions regarding this part. So this one, the linear discriminant analysis, is just when we talk about logistic regression, this involves directly modeling the probability of y given x. And then in the linear discriminant analysis, we are actually modeling the distribution of predictors x separately on each of the response classes. So which means we are actually going to predict the values like here. We estimate the probability of y equals to k. We predict the values probability of x given y equals to k. So we predict these values here. And then we use the base rule to flip those around, and then we get this number. So why we are going to use LDA? LDA, when the classes are well separated, LDA estimate parameters are more stable. And then LDA also performs well when the observation is small. And like when the distribution is specified, but there's few observations, the LDA help us to learn the discriminant directly rather than just based on the observations. And then LDA is more stable for the 2+ response classes. So when we have more than 2 response classes, it is more stable for the LDA estimation. And the base rule will be the essential part for the LDA method. So you need to be familiar with this base rule. So this is the initial part, which is probability of y given x times probability of x equals to the probability of y times the probability of x equals given y. And then this probability of x, this one is equals to the probability of x given y times the probability of y. For all of the case for each y choices. This is just discrete form for the base rule. And so when the parameter equals to 1, we only have one predictors. I'm sorry, not parameter, we only have one predictors. This will be the conditional probability density function of x. So we are going to have the expectation of this mu k represents for the expectation of y, the expectation value of x given y equals to k. And this sigma k here represents so sigma k square represents the variance of x given y equals to k. And then you can use data to estimate those values and then plug back into this function. And so this is the density. This notation represents the conditional probability density function of x given y equals to k. And then we plug this function back to the base rule, which is this function. So we plug this part into this part, and then you will get this results. So how we generate the LDA classifier? So we take the log form of the above equation. We take the log form of this equation, and then you can see we will have the log of this part minus the log of the denominator. It's just a calculation rule of the log. And then, so this part, the log of the pkx is proportional to the equation below. Every time when you do the log regression, we are going to talk about the LDA classifier is based on important parts. Like here, we are interested in the case when y equals to k, how the x perform in this case. So we only care about like the case, the elements that related to the y equals to k. For all the other things like y equal to y equals to L and other numbers like L plus 1, something like that, all of those numbers are irrelevant from the classifier. It's like a constant. So we have the classifier, this one is proportional to this part. This part is just when you take the log form of numerator and then log probability of y equals to k will be this element here, and then log of the 1 over the square root of 2 pi times sigma, this part will be constant, so we get rid of this part, and then you will have only the elements in this parentheses. And then when you do some calibrations, you may notice that x squared divided by 2 sigma squared is constant as well. So you will get the x squared in this parenthesis. So you will left with these two elements. And then we use this one to build the LDA classifier for y given k. I'm sorry, given y equals to k. And so for example, when we have k equals to 2, which means we're going to have y, 2 choices for y. And then the probability, we assume the probability for, we assume the probability of y equals to 1 and y equals to 2, they are the same. We give this assumption. And then we have the LDA classifier as this one. So we will have, so we plug in all of those numbers. So you will have x times mu1 divided by sigma2 square, sigma square, and then plus the pi 1 here. This is the first classifier. And then this will be the second classifier. Then how we classify if the observation is assigned to class 1 or 2. So we assign an observation to class 1 when we have the classifier 1 is bigger than 2. And then when you do delta 1 bigger than delta 2, this will give you the results something like this one. So when this number is bigger than this one, then we are going to assign the observation to class 1. So otherwise, we are going to assign the observation into the second class. Okay. And then in this case, how we calculate the base decision boundary. So we want to calculate the value of x here in this case. So we use x is equal to this one divided by 2 and mu1 minus mu2. So this one will be the base decision boundary. And the reason for this is get rid of this part is just because mu1 square minus mu2 square, this one equals to mu1 plus mu2 times mu1 minus mu2. And so they cancel each other and then get rid of this part in the denominator. Okay. And for the LDA approximation in the practical class, so in the real world, they will use this regression, this method, like use this part, this function to calculate the estimated mean of the observations. And this part is the variance is the sample variance for the data set. And then this one, pi k, this one is just going to talk about, here, it should be nk here, sub k, n sub k. So this is just property of the, like when y equals to k, what's the probability for y equals to k in the whole sample. Okay. And then you plug all of these numbers into the classifier to get this one, to get estimated classifier. So this is the case when we only have one parameter. So when we have two parameters or like 3 parameters, we are going to have a covariance matrix instead, rather than, so for here, we are not going to, you cannot get rid of those parts like just as neat as this part. So you will need to use the capital sigma to replace the small sigma here. It will be a covariance matrix, and then you do the same thing, follow the same algorithm. You will get a classifier as we have introduced before. And then, so that's how when the P is bigger than 1. And then you can refer to the page 143 in the textbook for detail. Okay. Any question? Okay, so that's all I'm going to cover this week, and then I will let the professor assign the homework on campus.